Now, in the last lecture, we had got the expression for the BCS coherence factors, namely for these probabilities Vk square and Uk square. So, Vk square was 1 minus half into 1 minus Ek over Ek square plus delta square, and Uk square is half of 1 plus Ek divided by square root of Ek square plus delta square. Okay, we have not of course calculated delta, but we will do that subsequently. But what you can see is that delta is some energy scale in the system. It is a very important energy scale, and Ek, if you recall, is the energy of the particle measured with respect to the Fermi energy. So it is Ek minus Ef, which is h cross square by 2m k square minus kf the whole square. Okay, so this is the energy of the particle in momentum state k measured with respect to Ef. So if I look at Vk square, then this is equal to half of 1 minus Ek minus Ef divided by square root of Ek minus Ef the whole square plus delta square. So note that at Ek equal to Ef, the Vk square becomes equal to half. Okay, so the probability of occupancy, okay, of this k prime state becomes equal to half. This is the probability of k up minus k down state being occupied. So at Ek equal to Ef, okay, right at the Fermi energy, the probability of this occupancy becomes half. Okay, that's interesting. And what you can see is that if Ek becomes, if you take Ek equal to Ef minus delta, okay, and if you put that into the expression, then you will get, if you put this in the above expression, if you take this Ek equal to Ef minus delta and put it in this, you will get Vk square as equal to approximately 0.853, which is approximately close to 1. Okay, so if you are at minus delta below the Fermi energy, okay, with respect to the Fermi energy, the occupancy of this becomes almost 100%. And if you are at an Ek which is equal to Ef plus delta, then you will get Vk square, which will be equal to about 0.146, which is of the order of 0. It is approaching 0. So here, so if you are at plus delta, the probability of occupancy of the k prime state, k minus k state, then that probability goes to 0. Now I must emphasize here that all these calculations are being done at 0 temperature. There is no effect of temperature included anywhere in the calculation. So this is an absolute must for you to remember, that we are looking at 0 temperature calculations. And here we see that at 0 temperature, the probability of the occupancies itself is changing around the Fermi energy. So if I look at the plot of this Vk square, so if I look at Vk square around the Fermi, so if I look at it as a function of energy, then it is 1. This is half, and let's say this is at Fermi energy. I am exaggerating it. This is Ef minus delta, and this is Ef plus delta. So at 0 temperature, this is the probability that k up minus k down state is occupied. It is 1 far away from the Fermi energy, which is expected, okay, very much farther away from the Fermi energy, this will approach 1, okay. But as you come within plus minus delta of the Fermi energy, this occupancy goes down, okay. This occupancy starts decreasing with respect to 1. Now if I draw on this the distribution, the Fermi-Dirac distribution for single electrons at 0 temperature, you remember that the distribution for the Fermi-Dirac distribution of single electrons at 0 temperature is basically going to be 1 up to the Fermi energy and then going to drop to 0. This is because up to the Fermi energy everything is occupied. So at t equal to 0, this is at t equal to 0, the Fermi-Dirac distribution, okay, FD. The Fermi-Dirac distribution is that it is going to be 0 up, it is going to be 1 up to the Fermi energy and above the Fermi energy. So this is where, if you recall this picture, that everything below the Fermi energy is occupied and everything above the Fermi energy is empty, okay. This is at temperature T equal to 0. But now what you see is that in this picture, what you start seeing is that here, even at temperature T equal to 0 around the Fermi energy, there will be a region around the Fermi energy within delta of the Fermi energy where there will be states and there will be vacant states. Because below the Fermi energy, if you will create vacancies below the Fermi energy, this part where your Vk is decreasing with respect to the Fermi-Dirac distribution, this is where holes are created below EF. Because this is an energy below EF and the distribution is falling below. It was in the Fermi-Dirac distribution, it is 1. So here you are creating vacancies below EF, and above EF, at energies above EF, you are creating occupied states, okay. So you are creating occupied states which are shown by these red dots, okay, which are present above EF, and these are holes which are creating. So you are creating empty and vacant states, and remember all of this is happening at T equal to 0 Kelvin, okay. So you are creating vacant and empty states around the Fermi energy right at 0 temperature, and this is coming because of interactions. The interactions, your Vk prime interactions that you have created inside the system, it is responsible for creating this sort of a distribution. So at T equal to 0, at T equal to 0 Kelvin, the EF becomes smeared out because of Vkk prime interactions in the system. So right at T equal to 0 Kelvin, you have vacant and occupied states which are created above and below the Fermi energy, and then the scattering between these states automatically comes into the picture. Okay, that is what was the part of your BCS Hamiltonian. The Vkk prime was basically taking you from occupied states to empty states and vice versa. Those were the states which are scattering in between, and the distribution is just reflecting that property of the system which has come about because of interactions. So whereas the Fermi-Dirac distribution was for non-interacting electrons, the moment you include the interaction, you see this change in the distribution. Okay, so this is a very important property of the system. And what you can also see is that, so if I plot again the Vk and Uk together, so you will see that this is 1 and it will go to 0. Okay, so this is 1, this is Vk square, it is 1 and it will go to 0 over Ef, and this is 2 delta Ef minus delta Ef plus delta. And what you can see is that if you look at the plot of UK, then the plot of UK is going to be 0. That means that the probability that k prime will not be occupied at energies far away from the Fermi energy is expected to be 0. But the moment you approach this plus minus delta, because these states are moving, so the occupied states are going to vacant states, so therefore the probability of them being vacant will start increasing. It will cross half and then it will do this. Okay, so far above the Fermi energy you will of course have vacant states which are going to be available. Okay, so this is going to be 1 for the green is for UK square, the green is for UK square. Okay, so this is the probability that the state k minus k is occupied, and this is the probability that the k minus k is vacant. This is the probability that the k minus k state is vacant. So that is going to be 0 far away from the Fermi energy, but the moment you start approaching delta, you start causing this excitation and you are causing scattering from k to k prime states, and so you are creating vacant states and occupied states around the Fermi energy, and that is why Vk square falls and Uk square picks up. Okay, so the probability of having vacant states around the Fermi energy increases until well above the Fermi energy there are anyway vacant states which are already present. So this is a very important topic of this is the coherence factors. Okay, and you can see what is the basic picture, okay, of BCS theory, and remember this is all at 0 Kelvin. Okay, so now let us continue the derivation and complete the last aspect of the derivation. Okay, so if we consider UK and VK, so now let us consider we had got UK square and VK square. So now if you take the product of UK square and VK square, it will be 1 by 4 1 minus EK square divided by EK square plus delta square. Okay, and so this will give you Vk into UK. Your coherence factors will be half delta by capital EK. So through different ways, you have also seen this earlier in terms of the cos and cosine functions, okay, and the sine functions when we had found out UK into VK. Okay, this was the same expression, but now using the factors that we had derived earlier, you get the same expression. Okay, now if you recall that let us try and derive how much is this delta, how much is this energy value delta, this energy scale delta that we have obtained, how much is that? If you recall, this was V0 by 2 summation of k prime sine 2 theta k prime. Okay, so this is nothing else but V0 by 2 summation of k prime sine theta k prime cos theta k prime. Okay, so this is your delta. Okay, so this delta is nothing else but V0 summation of UK prime VK prime. Okay, summation over k prime, which is nothing else but delta is equal to V0 summation over k prime. This is all over k prime. UK into VK we have already derived. This is delta over EK prime. Okay, and therefore since delta is independent, we assume is independent of the momentum state k. This is 1 is equal to V0 by 2 summation over k prime 1 by square root of ek prime square plus delta square. Okay, because ek prime is nothing else but this. Okay, square root of ek square. And now recall from condensed matter physics, if you are taking summation over all momentum states where all these momentum states are around the Fermi energy, remember these are the momentum states around the Fermi energy. So these are all these states. Okay, so if the solid line is your Fermi energy, you are looking at all the states which are within h cross omega d of the Fermi energy. You are basically looking at only these states. Okay, you are looking at only these states which are around the Fermi energy. Okay, now summation over all this is equal to, you take it as integral of g of e dE, where g of e is the density of states. The summation over k is integral g of e dE, which is the density of states. Okay, and this will be nothing else but where you are around h cross omega d of EF, you are going to do the integration around h cross omega d of EF. So it is EF minus h cross omega d to EF plus h cross omega d, and the density of states g of E will be approximately the density of states at the Fermi energy. You will approximate that the density of states, because h cross omega d is much less than EF. Remember that h cross omega d will be much less than, so your density of states, although I have exaggerated in this diagram, it's not such a thick band. It is almost, it's a very thin region which is around the density of states. So you will approximate the density of states as GEF. So this summation over the different momentum states can be taken as integral over all these density of states. Okay, so because that will give you all the states which are present around the Fermi energy, which is what you are taking a sum over, which is the same as just integrating it over these density of states, where the density of states is that at the Fermi energy. So with this, your above expression, this expression, so by doing this summation, our above expression now can be transformed into an integration, where I will write this as 1 equal to V naught into density of states at the Fermi energy. I have taken it out of the integration sign, EF minus h cross omega d to EF plus h cross omega d, d of E divided by square root of E square plus delta square. Now I can take E prime is equal to E minus EF. Okay, I can change the variables to this, then this will imply dE prime is equal to dE, and my upper and lower limit EF minus h cross omega d, for E equal to this thing, E prime would be minus h cross omega d, and for E equal to EF plus h cross omega d, E would be plus h cross omega d. So with this change of variable, 1 is equal to V naught g EF by 2 integral of minus h cross omega d to plus h cross omega d, dE divided by square root of E prime square plus delta square. This is anyway just a variable. Okay, and this is nothing else but V naught g EF by 2 into 2. Now for this symmetric function, 0 to h cross omega d, dE divided by square root of E square plus delta square, and this would be, you can show that this is of course sine, okay, so before, instead of going there, 1 is equal to V naught into GEF, density of states at the Fermi energy, into sine hyperbolic inverse h cross omega d by delta. Okay, and this can be simplified okay, and you can show that delta is equal to twice h cross omega d. Wait, let me write it clearly. If you just manipulate this expression, you can show that delta is equal to twice h cross omega d e raised to minus 1 over 2 over, sorry, this is minus 1 over V naught into GEF. This is from this expression you can come here, okay, and this is for the expression that V naught into GEF is much less than 1, or it's very small, okay, it is much less than 1. Then you can simplify this and bring it to this form, okay. And this is, if you recall, when we had solved, if you recall, the 2 electron problem interacting with attractive potential. If V naught was attractive, then the binding energy of the 2 electrons was exactly this. So we have obtained the energy scale delta, which is the binding energy associated with this Cooper pair, okay. This is essentially the binding energy of the Cooper pair, okay, and we have recovered that expression for this multi-particle system. For the multi-electron system, we have obtained the value of delta, which is twice h cross omega d e raised to minus 1 by V naught is the attractive interaction potential, and GEF is the density of states at the Fermi energy. So we get the energy scale delta. We calculate this energy scale delta, which, if you recall, for the 2 electron problem was related to the binding energy of this Cooper pair, okay, which we have obtained, but we will interpret it further, okay. This energy scale delta, we will interpret it as further in the next lecture.